of theory is just quantum notation for, in this case, the particular combination of DFT functional and basis set. And then we're going to talk about two of the most common applications of quantum in life sciences, and that includes reactivity and pKa prediction. All right, so introduction. So what is quantum and when is it appropriate to use? So you're going to need quantum day-to-day when you want higher accuracy and reliability of your results in comparison to, let's say, all atom molecular mechanics methods. It's also useful when you're studying conformations involving less common chemistry. Remember, molecular mechanics is highly parameterized, so if it's looking at something it hasn't seen before, it might not do so well. So if you're looking at something less common, you may want to look at quantum as well. Obviously, the other caveat with molecular mechanics is that it's highly parameterized, with the exception of reactive force fields, to look only at equilibrium geometries. So when you want to start studying things at non-equilibrium, QM is also a good go-to method. Transition metals are another area where molecular mechanics is likely to have a hard time, so we often use quantum there as well. With the exception of reactive force fields, all reactivity calculations I personally highly recommend using quantum. And then there are, of course, some more electron-heavy properties, for example, relativity, infrared spectroscopy, BCD, and so forth, that you also want to study with, let's just call it, an electron-aware method. So here's one example of a torsion scan where I want to show you what the effects of trying to use molecular mechanics to study non-equilibrium geometries. So if we look on the x-axis, what I'm showing you here is the rotamer of this molecule shown in the top left corner, where what we're doing is just rotating around that dihedral that is shown. And then on the y-axis, we have the energy in kcals per mole, because obviously I'm an American, so I apologize for those units. Then at the top, you can see that we've labeled the various methods used. So the black line is coupled cluster singles, doubles with perturbated triples at a complete basis set. So this is the gold standard. We take this to be the right answer. So what you want to do then is ask how all other methods line up compared to this. So you can see that when we do a relaxed rotational scan, so we go around that dihedral angle and run an energy minimization at each step, holding that dihedral constant, molecular mechanics does okay. However, when we do a rigid scan, that is, we go around that dihedral and simply take the single point energy at each point, do not do a relaxation at that stage, everything does not go so well. And the reason for that is molecular mechanics basically falls apart when you're studying non-equilibrium geometries. So in this case, you may elect, for example, to look at a quantum method, in this case, DFT. Why would you want to do that when I already told you that the gold standard is using coupled cluster? Well, the reason being that coupled cluster is very, very expensive to run. And if you want to know the numbers, I'd be happy to tell you those. But what we see is that DFT, in this case, does a much better job of approximating coupled cluster as we go out to beyond equilibrium geometries. So here's another example of when quantum might really help you out. So on the left, I'm showing a very complicated natural product. You can take this natural product, convert the structure to 3D, run a molecular mechanics-based conformational search. In this case, we're using the OPLS-3 force field, and take the 10 lowest energy conformations as predicted by molecular mechanics, and at the end, extract only the lowest energy one. Conversely, you can also take that same conformational ensemble of 10 and run an optimization using, in this case, quantum, where we're going to use DFT, in particular N062X, and take the lowest energy conformation from that. And the results would look something like this. So I'm showing you the molecular mechanics geometry in green, the density functional conformation in orange, and the experimental X-ray conformation in blue. So what you can see is when we come to really complex structures with bond angles and dihedrals and things that molecular mechanics may not be parameterized to deal with necessarily, it starts to fall apart, and we really want to start using a higher order method. Transition metals is another great example of when a lot of force field-based methods fall apart. And there's some trick to get this to work, and they are tricks that I usually employ, but suffice to say, as quantum calculations have gotten faster and more facile, you might just elect to do quantum instead. So you can see in this case, we have a transition metal complex. If we take the 2D structure and prepare it in 3D, you can see that we get something that just looks weird. Conversely, if you just run a quick calculation with DFT, you get something that looks very reasonable instead. And that's shown over on the bottom right. And so then on the bottom left, I'm showing you the X-ray, and so hopefully it's clear to you that the bottom left matches the bottom right. That is, the experimental structure looks most similar to that derived from DFT. So what are we doing in quantum? Well, all we're trying to do is seek a solution to Schrodinger's equation, where we have a Hamiltonian on the left, which describes the system, and that's different for every molecule. And then we have the wave function and the energy. Now, of course, inspection should convince you that we are looking for the energy E and the wave function simultaneously. So we have one equation and two unknowns, which means that we cannot solve this exactly. So what we're trying to do then is come up with various approximations to solve the Schrodinger equation. And so some of those are listed here. So Hartree-Fock is supported in our software, as well as local MP2 and, of course, DFT, which will be what we talk about primarily today. So how does DFT work? Well, it's not that complicated. You are first going to draw in a structure, or if you're feeling very ambitious, you can type in its coordinates. And then you're going to specify the flavor. So this is sort of the bread and butter of any quantum calculation. And then we specify what type of calculation we want to run, various properties we want to compute, and any additional options. And then what Jaguar, in this case, is going to do on the back end is try to go through and solve the self-consistent field equations to get at the energy and wave function. Remember, we cannot solve this analytically. We're going to have to go and do this iteratively, which is what it's going to do. Now, of course, sometimes your SCF will not converge and no results can be obtained. And there's various ways to get around that. And then finally, at the end, the properties will be computed and printed out, including the energy and anything else you specified. So let's talk now about level of theory, because it's really important that you are selecting in any calculation the appropriate basis set and functional, or your results might very well be meaningless. So returning to the previous workflow, what we're going to focus on is right here, steps 2 and 3, the functional that you want to use, as well as the basis set. So functional is a really funny word. So all functional means is that we are taking a function of a function. So in this case, we are taking the electron density, which is a function of the coordinates in, let's say, XYZ space, and we are dumping those into another function, and that function is, let's say, B3LYP. And all these functions do is try to approximate the Schrodinger equation in various ways. So DFT is one of these funny methods that is, in principle, fully ab initio, but in practice is not. And what I mean by that is the functional form of DFT is analytically known except for the exchange correlation term. So what we have to do is approximate exchange correlation. And that's what we're doing here with various functionals. So B3LYP, or as I like to call it, B3LYP, approximates exchange correlation differently than does M062X and so forth. So we take the electron density, we create a function of it that describes exchange correlation. Once we pick our functional, we want to pick a basis set that is best matched to that functional and to the property we wish to calculate. So basis sets might be, these, again, funny terms that you're used to hearing about, 631 G star, 631 plus plus G star star. We like to say these because they sound funny, but also because it gives us job security when nobody knows what the heck we're talking about. In addition to that, there's various DFT functionals to choose from. So the basis set is what's going to give you flexibility in your electron density and wave function. This is what's going to allow your electron density to spread far out in space or be polarizable and so forth. Now, it might be very appealing then to go up to as high of a basis set as possible so that you could have as much electron density and flexibility as possible. I don't recommend that, however, because the higher the basis set, the more computationally intensive the task becomes. DFT is really, or the DFT functional is really the flavor of the approximation to the exchange correlation that you will be doing. And some DFT functionals are good for some things and some are good for others. So it's really important that you know which one to choose before you proceed. Because there is really no single DFT functional that is best for everything. There are some that are better than others, but there's no real go-to functional. So if we take the example of phenol, we can start to talk about the basis set as an atomic setting. Each atom in this molecule is getting a different basis set. So in this case, we may elect to use a small basis on the hydrogens. We assume we don't need to describe those very well on the nonpolar hydrogens. Conversely, we might choose a very large basis set on the hydroxyl because we want to confer to it some polarizability and long-range interactions. We assume it's going to form some hydrogen bonds and so forth. The choice of DFT functional, conversely, is a molecular setting. This entire molecule can only be run at one level of theory with respect to the functional. And then in this case, that would be M062X. Now, basis set notation looks a little something like this. So we can have up to, in this case, 2 pluses or 2 stars. Now, all the pluses tell you is that we are adding diffuse functionals. So these are longer range. They allow a greater spatial extent of the electron density. So this is important when you have, let's say, a longer range interaction like a hydrogen bond or a dispersion interaction. The first plus is applied to the heavy atoms, and the second plus is applied to hydrogen atoms. Now, the annotation with the stars or the asterisks is to confer polarization. So it gives more flexibility to the electron density to mush and squish, to be as scientifically rigorous as I can about this. Again, the first star is for the heavy atoms, and the second star is for hydrogens. So a good way to remember this is think of the star as d orbitals, which are polarized, and the plus as giving you more space. So that's your diffusion. All of this can be configured easily from the Jaguar graphical user interface. If you go to the Molecule tab, you will see that there's an entire basis set setting, and you can configure polarization and diffusion independently of the core basis. So when you're choosing your basis set, we recommend a workflow that looks something like this. First, it's important to understand the type of calculation that you're running. If you're running a single point calculation, that is, all you care about is the energy of the geometry that you input. You do not wish to actually change that geometry at all. You can pick a larger basis. The caveat here is you need to be certain that the structure that you are feeding in is a good structure. For example, I do not recommend running a calculation at the molecular mechanics level and then feeding that geometry to a quantum mechanical single point calculation, because I generally don't have faith that the geometry that comes out of that will be good enough for quantum. Conversely, if you do want to run a geometry optimization, you want to make sure that all of your bond angles and lengths and so forth are in the good position. You might do this by picking a smaller basis set, because this is going to be a longer calculation. And so what you will see is throughout the geometry optimization, the energy will start to go down as we iterate through, and that's what we're showing in the graph in the bottom, where we have energy on the y-axis and the iteration of the geometry optimization calculation on the x. So finally, at the end of the calculation, this will converge. This will converge to a geometry that, in this case, DFT thinks is the right geometry. Now, once that is done, then you may wish to take that geometry, which is now a good geometry, and feed it into the single point calculation where you would use a larger, presumably better basis set to get at the energy. And what this does is this allows you to get at a geometry that looks good and an energy that is good without having to do everything at a really super high level of theory. So let's take, again, another big, scary macromolecular looking structure, in this case, Taxol. So in this case, what you may wish to do is run your geometry optimization using, let's say, 631G star star, and then once that is completed, transitioning to a larger basis set, let's say the Dunning CCPVTV minus F basis. Now, what I want you to do is note the number of basis functions that are here. We are still in the thousands of basis functions. This makes this a very large calculation, and it can be prone to convergence issues. So this is why it's really important with quantum calculations to be prudent in the size of the system you wish to carry forward. So let's consider this structure. In this case, what we're going to want to do when we're picking a basis set is find something that's reasonable. So let's say in this case we picked the 631G basis to describe all of the atoms that I've highlighted in blue. And then we would add polarization functions for elements heavier than neon, in this case the two sulfurs. And we're doing that because they're heavier atoms. We assume that they are going to have a more polarizable electron density. And then finally, we like to make sure that any anions are sufficiently diffuse in their electron description because we know that those are going to expand more out into space. So what we would do then is add diffuse functions to the anion here. Now, of course, cobbling together such a mixed basis set may not really be practical. So what we want to do in this case instead may be simply to define one basis set for everything that, yeah, it's a little bit large in some places, but at least it makes our life simpler with its consistency. So if you did want to define a mixed basis set, that can be done easily in the Jaguar input file, like so. You just have to go manually edit the atomic section. Now, the other thing that we want to convince you of is that the particular results that come out are extremely sensitive to the basis set and functional that you use. So consider this molecule where we know from experiment that the bond length is 1.587 angstroms and the angle is 98.048 degrees. If you run this using a very small basis set, you're going to get something that looks like this. It's really not quite accurate. And as we move up in our basis set size, what you can see is that this is converging to something that recaptures the experimental numbers. The same can be said for oxide anions. So here you see the bond lengths of these various anions. And again, as we go from a small basis set to a larger basis set, things start to recapitulate experiment. Again, remember though, as you move to larger basis sets, your computational time increases dramatically. Another situation that is really common is people want to use quantum methods to study dispersion. And this is a great idea because dispersion interactions are not explicitly parameterized in any force field, at least to my knowledge. They can be handled implicitly, but they are not explicitly accounted for. So dispersion interactions with quantum is a really common application. But here what you're going to want to do is again add diffuse functions to your basis set to make sure that you're capturing these long-range interactions that we know occur in dispersion-bound complexes. So let's have a fun exercise. Which of these basis sets would be good for studying this interaction? Remember, I told you you must have dispersion. So in this case, only answers A and B would be appropriate. Now, I'm sorry, A and D. You might think that B is appropriate because you would say, well, that has dispersion interactions. And you're right, It does, but only on the heavy atoms because it only has one plus. And if you look at this picture, what you can see is the hydrogen is actually pointing to the other benzene ring. So we need diffuse functions on all atoms in this case. So there's a lot of different basis sets to choose from in Jaguar, and it could get really confusing. So these are divided into a few categories, which are shown here. The Dunning basis sets include polarization implicitly. And then we have a number of effective core potentials, which are helpful if you want to study transition metals. And what this does is package all of the core electrons in the transition metal into an effective core potential, so you don't have to worry about them. You only worry about the valence electrons. So, and the two that I'm showing you right here, 631G star and LACVP, are the defaults in Jaguar when you are studying organic and inorganic systems, respectively. So setting 631G star is equivalent to setting 631G is equivalent to setting 631G with 6d orbitals for all of the elements in the periodic table that I'm showing circled in the top left. Conversely, setting LACVP is equivalent to setting 631G, this time with 5d orbitals for all of the elements I'm showing circled in the periodic table in the top right. And then for any heavier element, we start to add a larger basis set. So LACVP with effective core potentials or LACV3P with effective core potential. So what this means to just cut through all of the quantum parlance is that really for most practical applications, if you're studying a strictly organic system, setting LACVP is basically equivalent to setting 631G. So it won't hurt you just to use LACVP if you are uncertain. Now, when you open up the Jaguar graphical user interface and you go to select your basis set, you may notice these little PS icons next to the various basis sets that are listed. And what this is pseudospectral. So pseudospectral is just a way to numerically approximate the two electron integrals. Now, why would you want to do that? It's simple, it speeds up the calculation. DFT calculations scale as n cubed, where n is the number of electrons. So if you have n electrons and you double the number of electrons, you're going to see a cubic increase in the compute time required. Conversely, any basis that uses pseudospectral methods, that scaling goes down to n squared. So you save an order of magnitude in your computational cost. So different basis sets offer different analytic and pseudospectral coverage. So for example, those elements which I'm showing in blue are covered analytically, whereas those that are shown in red are covered pseudospectrally in the two basis sets shown. So here's the basis set selection workflow. If you're running a single point calculation, you want to use the larger basis set, as stated before. If you're doing a geometry optimization, you want to use a smaller. If there are negative charges, you're going to want to add diffuse functions, and that is also true if there's dispersion interactions as well. And then finally, if you're studying any of these heavier elements where we expect them to be more polarizable, you're going to want to add polarization functions too. Now, level of theory. If you open up the Jaguar graphical user interface, GUI, you'll see that we support 3 different levels of theory: density functional theory, DFT, Hartree-Fock, and LMP2. I really do not recommend using Hartree-Fock. We all learned Hartree-Fock theory in graduate school, but DFT is really much more accurate and not much more expensive. Hartree-Fock exists in the code still as a benchmark, sort of a legacy thing. Now, LMP2 used to be quite a bit more accurate than the DFT methods that we had in there, but with the newest DFT functionals that have come online in, let's say, the last 5 to 10 years, I would honestly just recommend sticking with DFT in most cases. So if we look at the functionals, again, they're categorized as the following. And we use these terms like local density approximation, gradient corrected, and so forth. Remember, all these are different ways to approximate the exchange correlation term. So these are just the ways that is approximated, and then listed within these is various flavors of that approximation. All of these functionals can be found right here in the GUI. And what we've tried to do is not overwhelm you and make it clear which ones we recommend using and which ones are just there in case you might want to run them. So if you open up the panel, you'll notice the very first thing is that B3LYP, or B3LYP, is the default. That does not mean that we recommend running B3LYP most times. It is the default because it's actually legacy. B3LYP has been the most popular functional for many, many years. But there's a lot of really excellent functionals that you can see we've shown you here instead because they have really important use cases as well. So here is the quick and dirty breakdown. So the local density approximation is something we don't recommend you use in most practical calculations. It's really been supplanted by some of the other methods that are shown here. In particular, the hybrid methods, as well as something called an a posteriori corrected functional, which is what I did for my PhD. And again, the important thing to remember is there's no universal functional for all purposes. So I'm showing you over here on the left various properties that you may wish to calculate, and then the functional that is the best, average, and worst for that property. So what I want you to do is hone in on M062X. This is another really popular functional alongside B3LYP. And you can see that it's really, in some cases, the worst possible functional you could use to study a property of interest. Sometimes it's the best, though. So when do you want to use which? So B3LYP remains really good for geometry optimizations, nuclear magnetic resonance, polarizabilities, and frequencies, whereas M06 remains really good for properties and energies of structures with 3D metals. And M062X is really good for calculating enthalpy of formation and energies. The a posteriori functionals were really developed to describe non-covalent interactions, things like long-range hydrogen bonds, dispersion, and so forth. And some of those are listed here. So PW6B95, for example, is sort of the best compromise between accuracy and stability, and so forth. So what is an a posteriori corrected functional, and why has this become popular in the last 5 to 10 years? So basically, people went and looked back in the DFT literature and decided that everybody was spending all of their time trying to rewrite the exchange correlation approximation, and nobody had really succeeded in making anything that was very robust. So instead of trying to rewrite it from scratch, what various people decided to do was take a functional that was already relatively good and just add a correction to it. And so that is what you see here highlighted in red, D3 and MM. So the D3 a posteriori corrected functional came from Stefan Grimme, and it is specifically to correct for dispersion. And then the MM correction actually came out of the Friesner lab at Columbia and is to do the same thing. So why is this important? So I had a customer come to me and he told me that he was trying to run an optimization of benzene dimer, exactly like I'm showing you here. And of course, he trusted us to have enabled him with proper settings in the graphical user interface. So he used the default, which in this case is B3LYP, and that's shown in red. And what you can see is as we move out to higher and higher distances, the benzene dimer just falls apart. B3LYP is not particularly good at dispersion. It doesn't even know that these two benzene rings should stick together. So he came to me bewildered why this was, and I explained B3LYP is a terrible functional to describe dispersion. However, you can move to an a posteriori corrected version of B3LYP, in this case using either the MM correction that came out of Columbia or the D3 correction that came from Stefan Grimme, shown in green and blue, and you can see that now benzene dimer does actually stick to itself. It is now dispersion aware. So, energy corrected functionals make dispersion interactions happen. So I am not very good at memorizing which functional and basis set is the best one to use for any particular property of interest. So this is my cheat sheet. I look at this anytime I'm running any quantum calculation to remind myself which method I want to use. Now, it's not like this is something that has been ordained from above. This is something that we've arrived at with a lot of benchmarks. So I highly recommend this is something that you keep in your back pocket. So B3LYP on the left, B3LYP-MM developed at Columbia, then B3LYP-LOC, which is the functional I developed at Columbia, and then M062X out of the TrueLAR lab, and then PW6B95, which we already talked about. So without further ado, I want to move on to two of the most important applications, one of which is reactivity. So you can imagine reactivity something like this, where you have reactants and products that are connected by a transition state. And the difference between the reactant and the transition state is the activation barrier. And what we want to get at is this transition state. Now, transition states, by definition, involve, and when we're talking about this in the small molecule world, I should say, by definition involve bond breaking and forming. Now, this is something, again, that a non-reactive force field is just not going to be able to get right. You're going to stretch that bond to infinite separation, and the energy is just going to go up, 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 and never go down to give you the products. So we have to use quantum to study this problem. And some of the applications of this might be predicting regioselectivity. So in this reaction that I'm showing you in the top left, we did a CH activation. We wanted to pop off one of those hydrogens on that aromatic ring, but we want to know which hydrogen the catalyst is going to target. So we calculated the transition states for all of the three positions shown, and we saw that the lowest barrier, the lowest activation barrier, was at position 2, and that corroborated with experiment. And the other time that you might wish to use quantum is predicting reaction pathways and mechanisms. How does that organic transformation occur? In this case, I'm showing you a transformation that could have occurred via one of two different pathways, the one on top in green and the one on bottom in red. And we can calculate the barriers for these steps and show that the pathway shown in green is in fact the lower energy pathway. Another way to use this method is to start thinking about rank ordering compounds by reactivity. So in this particular study, we were interested in studying a bunch of nitriles, where the nitrile would act as a Michael acceptor and a nucleophile would attack it. And it's not obvious to me, at least, maybe it would be obvious to some of the physical organic chemists out there, how substitutions on that ring would affect the rate of attack. So what you can do is take each one of these, run their transition state, and use that to rank order them by reactivity. And I'm showing you here a plot of the experimentally known reactivity versus that predicted rigorously from transition state theory. And finally, it's extremely important in catalyst design. So in this case, I'm showing you an inorganic catalyst where this is really a double problem for quantum. A, it's an inorganic system, so we know that the force fields aren't going to do very well. And B, it's a bond breaking and forming situation. So what you may wish to know in this case is which of these catalysts is going to be the most effective in doing the reaction of interest. And so you can go and plot the various activation energies, and those are shown in varying colors, where the purple activation barrier would be the lowest, and therefore would be the catalyst we may wish to target for design. So transition state searches have been a huge, huge pain. This is one of those things that is probably one of the hardest things to master, and I spent many, many hours doing it. The manual approach involves drawing a reaction, making sure that the atoms are consistently numbered between the reactants and the products, coming up with a guess of the transition state, refining that guess, finally finding that guess, and then validating that guess. This is very laborious. This is really suitable for experts only and is definitely not amenable to high throughput screening. So what we've tried to do is make that a heck of a lot less painful by developing an automated approach to find transition states. So if you compare it to the old workflow, everything after draw reaction we have automated using a nodule called AutoTS in Jaguar. So this is a really hard problem, automating it, that is. The potential energy surfaces are really complicated and unusual. You need to be able to support large amounts of chemical space, organic reactions, inorganic reactions, and so forth. The reaction mechanism may completely change depending on various substituents, and you have to deal with things like barrierless or uncertain reaction steps. Also, preparing entrance and exit complexes, these are called pre-reactive complexes or post-reactive complexes, is non-trivial. And so at Schrodinger, at least, this has been a massive engineering effort. And we think we're getting towards something that you guys would really like. So how does this work? In this case, what you would do is come up with a stoichiometric reaction of interest. It's extremely important that this be stoichiometric. Atoms cannot disappear and pop into existence. They must all be there in the reactants and all be there in the products. You would then use the graphical user interface to simply draw these structures in, the two reactants on the left and the two products on the right, again, being careful that stoichiometry is preserved. That is all you need. Jaguar will then go and do all of the heavy lifting for you. So you launch the transition state calculation, and it's going to attempt to form reasonable entrance and exit complexes. How do these two molecules approach each other to form the transition state, and how do they leave each other after the transition state is formed? And you can adjust these if you need. Finally, the transition state search will start, and hopefully a transition state is found. And then the transition state will be traced both towards the reactant and towards the product using an intrinsic reaction coordinate scan to verify that the transition state that is found indeed actually corresponds to the reactants and the products that you input. And then finally, the potential energy surface diagram is going to be printed, where I've got energy on the y-axis and reaction coordinate on the x, and you can see that we go up in energy to the transition state and then finally down to the product. Now consider, for example, the favorite reaction of any introductory organic class, which is a Diels-Alder. So it's very well known that there are two possible isomers that can come from a Diels-Alder reaction. One is exo, and the other is indo, where indo is the dominant isomer from experiment. So these could be run very quickly and were run very quickly using the AutoTS workflow in Jaguar, using, in this particular case, B3LYP-D3, 631G star star in the gas phase. This was done in a fully automated way. All we did was draw in the reactants and the two different products and ask what was the barrier. And those are shown here. So what you can see is that the transition state barrier for the indo isomer is in fact the lower energy barrier, whereas that for exo is higher. And this only took a couple of minutes to draw the structures and start the transition state calculations, compared to doing this even a few months ago, where you would have most likely wanted to go to the literature and find some transition states that somebody had already converged, pull those from their supporting information, and use those to guide you in a very manual process. So here's a set of reactions that we've actually been working on in collaboration with the guys at Pfizer in Boston, which is why I'm talking to you. So they're particularly interested in studying this CH activation through this inorganic catalyzed reaction. So what we were able to do is arrive at this very complex transition state for them, shown here in the middle of the slide, in a fully automated way. Again, all we put in was the reactants and the products, and we let AutoTS do all of the heavy lifting. So to show you how this is done practically, again, we visit the graphical user interface, where all we had to do was draw in the reactants and the products, shown here. Now, for anyone who's ever been through this, I will say that drawing inorganic complexes is not trivial, but once you master that, you draw it in, you hit go, and everything else is done for you. Also in the graphical user interface, there are multiple options if you need. So for example, you can go through and alter the level of theory if you wish under advanced settings, as well as various other things that you may wish to play with. When the calculation is done, the results can also be visualized through a graphical user interface, where we try to plot out the energy as a function of reaction progress for you. And this is actually coupled to the workspace, so you can click on any particular point and it will show you the structure in the workspace as well. And I'm showing you here two particular examples where we wanted to predict which site on these bicyclic aromatic molecules would be the one that the catalyst actually targeted. So we calculated the activation energy at every single hydrogen on these heterocycles and showed that the various sites that I have boxed in green were in fact the ones that were the lowest energy barrier in agreement with experiment. And so what we can do is start to look at more subtle effects. So if you look at this series of reactions, what we're varying is the R group, shown here in red. And as we vary the R group, we find that the barrier height also changes. This makes sense. But you can also calculate the pKa, the acidity of that R group, and you can see that there's a really nice trend. So the other thing that might happen is if you're not certain that the transition that you're looking at from reactant to product is a single-step concerted mechanism, you may find yourself having multiple transition states and intermediates in between your reactant and your product that you did not anticipate. So an example is something like this, where we input the reactant and the product, assuming that there was only one transition state between them. Lo and behold, there's not. So we started with the reactant and this transition state was found. But it corresponds to a different product than the one we input. So what the AutoTS protocol will do is understand this and now treat this as the reactant and try to find a new transition state. Now we have the full reaction pathway and you never had to mess with it. Here's another similar example of an iterative transition state search. So to summarize for the auto transition state search, this is completely automated based in Jaguar, and it involves easy and intuitive setup. It greatly speeds up any research involving catalysis and reactivity, and this is projected for broad release in the middle of 2016. So I want to conclude by talking a little bit about pKa prediction. So pKa prediction is a really complex problem. It involves a lot of different things working together. Mesomers, tautomers, conformations, micro versus macro pKa, and so forth. So here's one of my favorite examples that illustrates why this is so complex. So let's consider the example of a proton sponge. So what I'm showing you here is a molecule where the pKa is really quite high. And the reason for that is you have these two amines which are facing each other. Their remaining orbitals are sticking right into each other, and you have really egregious steric clashes between the two. So what you can do is put a hydrogen between the two, and suddenly that clash is diminished. So here's a case where the molecule really wants to hold on to the hydrogen, hence the name proton sponge. And we know from experiment, which is shown in black, that that pKa is quite high. Compare it to its neighbor, where all we've done is add a little linker, and here the repulsion has gone down quite a bit, and the pKa is, of course, dropped. 1 over, we have yet another analog of this, where the steric repulsion has returned again, and thus the pKa is quite high, and so forth. Now, the black line corresponds to the experimental pKa, and the red line corresponds to that computed, in this case, using Jaguar's pKa algorithm. And what you can see is that if you were to use an empirical algorithm, in this case EPIC, you would absolutely get this wrong. It's just too subtle for EPIC to be able to pick it up. So here we want to use DFT-based pKa to correctly reproduce the experimentally observed trend, especially in this delicate electronic case. The other thing to consider is that this is extremely sensitive to confirmation. So I'm showing you on the y-axis the mean unsigned error of the pKa calculation versus experiment, and then on the x-axis the various methods that were used. If you just draw in your molecule using two different starting confirmations, you will get wildly different answers. However, going along the x-axis towards the right, you can see that as we do greater and greater amounts of conformational searching and take more confirmations forward to our calculation, the error in the calculation starts to go down. So it is important to do conformational searches and include several confirmations in your pKa workflow. Another example that I want to talk about is shown here. So the only difference between these two molecules is the stereochemistry of the fluorination. And what you can see is the numbers in black at the bottom of the slide give the experimental pKa, which is quite a bit different between these two molecules, in spite of a very small subtle effect. If you were to try to run this with the empirical pKa prediction, it would assume that they are equivalent. It's just too subtle for it to be able to pick up. Conversely, when you run this with DFT, you can see that it gets the answer quite right. Here's another example of some more subtle effects. So you can see on the top, the nitrogen is methylated. On the bottom, it is not. And you can also see that we are varying the stereochemistry of the hydroxyl. In all of these cases, the empirical calculation shown in green thinks that these are all basically equivalent, even though we can see that the numbers in black from the experiment vary quite a bit. And of course, Jaguar saves the day here. It understands the difference. And here's just this shown graphically, where the empirical EPIC pKa prediction is shown in green, experiment is shown in black, and you can see that that's best recapitulated by the quantum calculation shown in red. So to conclude, empirical methods are fast for calculation of pKa, but may provide large inaccuracies on complicated structures with uncommon functional groups. Conversely, DFT-based methods are slow, but they're really good if you want to study rare or uncommon functional groups, or maybe something that might be more subtle electronically. It's important to take multiple confirmations into account, as well as stereochemistry. So to conclude the talk, what we talked about is when is it appropriate to use QM. We also talked about various levels of theory, where hopefully I convinced you that there's no single best functional for any task. And the specific level of theory you want to use is a function of the task you wish to study. Reactivity is, of course, a very sought-after thing, and quantum is the go-to method to study that. And we have developed a protocol that we're starting to release more broadly that makes finding transition states much easier, and that has broad applications to reactivity and toxicity. And finally, we talked about pKa predictions, where hopefully I convinced you that quantum pKa calculations give a big boost over empirical methods in terms of accuracy, where obviously you will suffer a higher computational cost. But it is especially important where pKa may come from subtle electronic or steric effects. And that's it. I'm happy to take any questions.
Thank you, Michelle. Thanks a lot for this interesting presentation. Yeah, it is now time for Q&A. If you guys have any questions, please type them in the Q&A field, which is at the right of the screen. And some of you already found this this window, and I will start with some questions. Question number one, is it possible to predict fluorescence with QM?
Yeah, you would just need to do excited state, which I didn't talk about. So yes, if you go into the Jaguar graphical user interface, you'll find the TD DFT, so time-dependent DFT, which is good for handling excited states. So that's what you're going to want to use. It's just not something I talked about today.
Okay, thanks.
Yeah.
Second question. Combination of different basis sets is faster, but maybe is it better to use larger bases for all atoms?
It depends on what you want to do. It also depends, yeah, here's a really unsatisfactory answer. It depends on what you want to do. It depends on how much computational speed you have. Let's say I had a system where I really only had one atom that I thought needed to be treated at a higher basis set and everything else at a smaller, and I had limited computational resources. Then I might use a mixed basis set. However, if I had reasonable computational resources, I wasn't too afraid of parallelizing that, let's say, over the cluster, then yeah, I might just go with a larger basis set. Absolutely. It's something you can experiment with. There's no right answer.
Okay. Third question, is it appropriate to calculate the transition state without taking into account the rest of the system protein, at least with molecular mechanics? Is it a way of do it? What? Is it a way to do this with Jaguar? Sorry.
I think what they're asking is, actually, can you repeat it? I want to make sure I fully understand. Just the first part.
Sure. Is it appropriate to calculate the transition state without taking into account the rest of the system protein?
Okay, yeah, I understand what they're asking. So I think what they're asking is, here we're doing the transition state, let's say of an enzymatic reaction, but we're not using the entire enzyme. All we're using is, let's say, a model of the active site. So this is a really common method. We call it a cluster model, where what you do is you assume that what you're doing in Jaguar, so just these small little molecules, is a good approximation to the overall protein or enzyme complex. Now, if you don't want to do that, if you are uncomfortable with using a cluster model, what you can do is use QMMN instead. So we have a QMMN package that uses Jaguar. It's called QSite. It's just, I personally believe, harder to use and buggier in the sense that the chemical space that you have to search is a lot more complex. So in such cases, what I recommend you do is you do the cluster model first, and then if you're feeling ambitious, use that to go on to get the same transition state using QMMN.
Thank you. Next question. Is it possible to calculate transition state in presence of solvent molecules?
Yeah, okay, let's just talk about two different ways, explicit or implicit. So one thing I didn't talk about today was various implicit solvent methods in Jaguar. There are a bunch, and solvation calculations are something that is regularly done. However, like all things quantum, you really need to know which is the right method to use for what you want to do. So the two most recent implicit solvent methods that are in Jaguar include SM6 and SM8 that come out of the TrueLar lab. These, however, only treat water, if I remember correctly. So any other solvent that you want to study, you're going to have to use the Poisson-Boltzmann finite solver for that, which is notoriously not very good. So implicit solvent models for quantum calculations remain a really active area of research. And unless you are very certain that solvent is going to create a big effect, I tend to shy away from them. Now, there's no reason, and this is something that was done a lot by, I think, Ken Hauck, where he believed very strongly that there were a few explicit water molecules in this case that were going to have a big effect on the transition state. So what he did is actually just manually added a few water molecules to his transition states, and he saw that that had a big difference. And the one other thing I will say about this is if you are really wanting to use solvent, what I would recommend doing is running your geometry optimizations in vacuum, gas phase, and then only following up with a solution phase single point energy. And that's all I have to say about that.
Thank you. There's another question. Can the QM methods in Maestro be utilized for covalent docking, predicting a better small molecular binder, in brackets, from a set of few molecules to a specific protein? Yeah, absolutely, and I'm glad you asked. This is another thing that we've been working on with the guys at Pfizer, and this is an extremely common request. So in the case of covalent inhibitors, what you're trying to do is, for example, find the, let's say, Michael acceptor or electrophile that will react with, let's say, a thiol. So what you would do, or what I would recommend you do, is set up the various transition state calculations where the reactant is a lone thiol and your lone electrophile. The product is, of course, where the thiol is now covalently added to the Michael acceptor. And then you run this through the AutoTS protocol, getting the activation barriers at each step. So now
what's tricky about covalent inhibitors, and I'm sure you know this, is you want high reactivity to the protein, but you want low reactivity to things like glutathione. So what I would recommend doing is setting up two screens. One where you're running the calculation with, the cluster model of your protein active site, and one where you're running it with glutathione, and try to find those molecules which are hot against your target, your protein, but are sluggish against glutathione. All of these based on the various activation barriers that come out of AutoTS.
Okay, thank you. Next question, how can QM calculations improve drug design results?
This is a great question, actually. So I will tell you, I did my PhD in a lot of this stuff, and now I do a lot of drug discovery. And I find that I don't use it a lot. And that's because molecular mechanics is really the workhorse of a lot of drug discovery. So when do I use it? And I only use it when I feel it's really giving me a big boost. And that is in pKa. So I will use empirical pK a lot of the time, but whenever I see something that comes out of EPIC, which is what I use for empirical pKa prediction, it doesn't make sense to me, I will go and run it with Jaguar pKa. The other time I use this is anytime we want to study really unusual functional groups. Maybe I'm trying to convince a chemist to go and synthesize a molecule that's going to make a particular interaction inside a protein binding site. And it's a really weird functional group, one that the chemist may not want to do. So then I generally try to convince them that I'm not totally full of it by going and running the optimizations at the QM level and showing it to them. The other way that I've used this, and I think it's really helpful, is a great way to make a ligand more sticky to your protein is to add a really targeted, selective, potent dispersion interaction. So I've gone and run massive libraries where, let's say I'm interested in optimizing a pi-pi stacking interaction between a tryptophan side chain and my molecule. So I will find a massive library of, let's say, heteroaromatics and ask, what is the interaction energy between this tryptophan and every single one of those members of that library? And select those which have a really sticky, really favorable binding energy and try to incorporate those into my ligands. Hopefully that gives some guidance.
I think so. So we have
one more. Protein ligand binding of metals. So for example, consider HDACs. So HDACs have zinc centers. There's no way you're going to be able to optimize the binding to the zinc using a molecular mechanics method with any real fidelity. So I have done some studies on transition metal binding of ligands to the zinc in, for example, HDACs to try to optimize that interaction. Okay, I'm sorry, Francisca, go ahead.
Not to worry. Okay, we have, unfortunately, our time is up and we have only time for one last question. And we got this question several times, and I think this is for me to answer. The question is, can we get recorded versions of this webinar and other webinars held this week? The answer is yes, of course. You will get the link to these webinars, to the records. And the link will be provided by Monday the latest, when the bootcamp week is over. And you will all have access to this. And unfortunately, we have no time for further questions. However, we will answer all the questions that we collected from this webinar. We will answer them tomorrow, the latest, through email. We will get back to you. And yeah, I'm sorry for that, but time is up. Thank you, Michelle, for your time today, for answering all the questions. And yeah, I hope we can welcome you to all our other events this week.
Bye. Thank you.
Thank you. Bye-bye.